Hello and welcome to this introduction to forecasting. In this video I want to show you how to implement two fairly widely used forecasting techniques. That is the moving average, the exponential smoothing forecasting method, also known as the exponentially weighted moving average. And in another video I will talk about time series regression analysis. Now we're going to do this looking at a data set that comprises 100 weeks of data starting in week 12, all the way down to week 111. And ultimately, our objective, of course, will be to come up with a forecast for period 112. Now, as always, what I did was I plotted the data first just to see what's going on. Notice, of course, the usual degree of random variability, but in addition, I'm able to make out another pattern here. Notice how demand first increases up until about week 70 or so, then it kind of flattens out, and the trend converses. So this will be an indication of cyclicality. Remember, this is weekly data spanning about 2 years, so this cannot be seasonality. At any rate, if we have cyclicality, of course, we've got to question what would be appropriate techniques. And I can tell you right now, perhaps a moving average method, for example, would not be the very best technique to use in this case. But I want to use this data anyway, at least to illustrate to you how we can implement these various forecasting techniques. So let's jump right in and take a look at the moving average forecasting method. Specifically, we're going to calculate 3-period moving averages. We do this by starting out at the beginning of our data set. The first period for which we can actually calculate a forecast would be for period 15, because at that period we have 3 weeks worth of preceding demand observations. So accordingly, my forecast for period 15 will be the average demand observation across weeks 12 to 14. In this case, 272. And the good thing is I can simply copy this calculation all the way down, and I get an out-of-sample forecast for week 112 of 423 units. Now, the million-dollar question, of course, is just how good a forecast is this? Well, to answer that, I first need to calculate forecast errors. And the way I do this is I simply take the actual demand observation and subtract from it the associated forecast. So for period 15, for example, my forecast error would be negative 14, which means I over-predicted demand for period 15 by 14 units. Now I'm also going to calculate the absolute value of my forecast error by using the ABS function in Excel. You'll see in a moment why we need this information as well. Now I'll calculate these forecast errors for all the periods in the dataset for which I have an actual demand observation as well as an associated forecast. With that done, I can now calculate two commonly used forecast error statistics, that is, the mean absolute deviation and the mean error. Now the mean absolute deviation is simply equal to the average value of all my absolute forecast errors. In this case, we're looking at 36 units. What this means is that on average, my forecasts are off by 36 units. It doesn't tell me whether I tend to over or under predict. It simply tells me about the magnitude of my forecast errors. At the same time, I can also calculate a mean error, and the mean error tells me something else. But first of all, let's calculate it. It is the average of my nominal forecast errors. In this case, I'm looking at 3 units. Now to interpret this number, we need to think a little more carefully here. So recall that I calculated forecast errors as actual demand observation minus the associated forecast. So in other words, if I have a forecast error that is positive, it means that I underpredict demand. Likewise, if I get a mean error that is positive, it tells me that on average I tend to underpredict, or in other words, my forecasts are negatively biased. Again, this would mean that I tend to come up with my forecasts that tend to be lower than actual demand. So, whereas the mean absolute deviation tells me something about the magnitude of my forecast errors, the mean error tells me about the systematic bias in my forecasts. So it tells me two different things. Now let's move on to the exponential smoothing method. And then we'll be able to compare the different forecast techniques in terms of the forecast error statistics they produce. So in this case, we're going to be looking up an exponential smoothing forecast method for a value of alpha of 0.25. Remember, alpha is simply a weighting factor. Exponential smoothing simply is an extension of simple moving average. The difference being that I do not assign the exact same weight to each of the preceding demand observations. Rather, I calculate my forecast as the weight alpha times the actual demand observation in the prior period plus 1 minus alpha times the forecast for that prior period. And that forecast in turn, of course, will then again be equal to alpha times the demand observation in the period before that, plus 1 minus alpha times the forecast for that period. So again, you see how this is an exponential method in that I apply exponentially declining weights to my forecast calculation. It sounds complicated, but the good news is that it's actually quite easy in terms of the implementation. Now, before we can go ahead and calculate these forecasts, we need to seed our forecast. What this means is I need to come up with a forecast for week 12, which of course is difficult because I do not have any demand history prior to week 12. And so we have to make some assumptions here. One assumption would be to set the forecast, this hypothetical forecast for week 12, equal to the actual demand observation, which is 248. Other ways of seeding forecasts would be to take the average demand observation of the first 5 or 10 weeks worth of data. Now the good news is the larger the data set, the less it matters how exactly we seed our forecast. For now, I will simply make the assumption that our forecast for week 12 would have been perfect. In other words, it would have been equal to actual demand. Now with that done, we can go ahead and implement the exponential smoothing method. So again, it will be equal to alpha, which is 0.25 right now, times the actual demand observation in the preceding period, plus 1 minus alpha times the associated forecast. In other words, the forecast for the preceding period. Right now, of course, that's still 248 because actual demand and the forecast were assumed to be identical. However, I can again go ahead and copy down this calculation. You'll see that I get an out-of-sample forecast here for week 112 of 430 units. And again, I want to assess the quality of the forecast by calculating forecast errors. Now notice that I explicitly exclude the first period here, and that's simply because the forecast for week 12 was an artificial construct rather than a real forecast. So at any rate, my forecast errors will be actual demand minus the associated forecast. And again, I'm going to calculate the absolute forecast error at the same time. And again, I'll copy down the calculation throughout the remainder of the data set. Now I can go ahead and calculate again the mean absolute deviation, which is 36 in this case, just like it was for the simple moving average. And I'm also calculating the mean error, which is the average again of my non-absolute forecast errors. Now you notice that here, comparing the 3-period moving average with the exponential smoothing method for alpha equals 0.25, I'm clearly better off using the moving average forecasting technique. Now, of course, notice that these numbers here, looking at exponential smoothing, my forecast of 430, my mean absolute deviation, and my mean error, they are all critically hinged on the specific value of alpha chosen. So, for example, let me change the alpha to 0.1. Now you see my forecast errors are much worse than they were to begin with, so clearly I'm moving in the wrong direction. Let me set it equal to 0.4. Now you see I actually get a mean absolute deviation that is a good bit lower than it was initially. And it's even lower than what I could get using the 3-period moving average forecasting technique. However, the mean error still is a little higher than it would be using the moving average forecasting technique. Now clearly the million-dollar question is what is the value of alpha that I should use? It is customary to constrain alpha to be equal to somewhere between 0.1 and 0.5. If it's much more than that, the exponential smoothing method, of course, approaches something along the lines of a last period demand forecast, and then it really wouldn't make all that much sense. Now I want to show you how we can use the power of Excel to find a good value of alpha, with good, of course, being defined as a value that minimizes forecast errors. So let me pull up Excel Solver here. And what I want to do is I want to minimize my forecast errors. Let me minimize my mean absolute deviation. So that's my objective function that I want to minimize by changing the value of alpha. Now I'll impose a couple of constraints, that is, alpha should be equal to or lesser than 0.5. Again, this is typically true. And also alpha typically should be equal to or greater than 0.1. Again, those are just standard constraints that we typically impose. And now I click on Solve, and you can see that I find the optimum value of alpha to be 0.39781. In other words, my earlier guess of 0.4 was actually quite good. And now looking at the mean absolute deviation, only, I will conclude that the exponential smoothing method for an alpha of about 0.4 actually performs better than a moving average forecasting method. On the other hand, there's a trade-off here. I actually have a greater degree of bias using exponential smoothing with alpha of 0.4 than I would have using the moving average method. I'm going to end this presentation here, but I'll encourage you to come back for another video where I will talk about the time series regression forecasting method.